Hello, we're at Quillon Racing, and in our first year, we came 7th overall in the development category. We had a huge improvement drive, and then we came 4th overall in the pro category. We had an even bigger improvement drive, and now we aim to come 1st overall in the pro category. So, hi, I'm Trin Martins-Bradbury. I'm the lead engineer and time manager of the Quillon. I support Ferrari, and I'm half Portuguese, half British.
Hi, I'm Oscar Doyle. I'm the deputy engineer and the lead of graphic design. I support Red Bull Racing. I'm half Estonian, quarter Irish, and quarter English.
Hi, I'm Davan. I'm in charge of rendering and the pit display. I support the McLaren F1 team and I'm from India.
So today we're going to talk about 3 things, and that's collaboration, innovation, and we'll finish it off by talking about our learning experiences. We've innovated a bit on the form, how we're delivering to you this presentation. So halfway through the video, we're going to cut to some people to talk more about our innovations in a more hands-on perspective.
So this is a diagram showing our tasks. The other tasks include the pit display and the verbal presentation.
So the most impressive way about how we collaborated is our collaboration with a higher education institute, Heriot-Watt University. I'm going to hand off to Oscar to talk a bit more in depth about this.
We contacted Heriot-Watt and asked to visit their laboratory on campus. We brought this 3D printed car design and special modifications such as telltales so we could perform certain and unique experiments. We did 3 main experiments. First, we plotted the velocity against the drag. This allowed us to gain a drag coefficient and create a polynomial, so we could estimate the speed of the car along the entire race. Next, we also found how angle of attack affects the aerodynamic coefficient. So how much the car tilt affected our speed, so we would know how much to minimize that while we're racing. Lastly, we used pitot tubes to find the pressure and wind speed at certain areas in the car. This allowed us to compare the real-life results versus the CFD results, so we could find which CFD solver was the most optimal for our purposes.
And about the project outcomes and the links to learning of this, as Oscar mentioned, we were able to see which CFD software was the best, which is particularly useful because if we look at this, Autodesk gave a force of 0.34, ANSYS 0.32, SimScale 0.41, and previous runs of Autodesk gave us even lower at 0.2 something. So doing this really helped us because we were able to pick which software gave us the most accurate results, and this is further improved by these things which are called telltales or tufts, and they vibrate when it's in turbulent airflow. So you see this is vibrating, that's a turbulent airflow, which aligns with SimScale, what it told us, and the back ones are all laminar, which is due to our well-designed car.
So these are some of our sponsors. D-Grade provided us with recycled t-shirts made from water bottles. ANSYS was the CFD software, and Riot provided us with the pit display. Our secondary sponsors was Heriot-Watt University, SimScale, and we represent Double Lily School.
I just want to add that Riot, we would have had the pit display supplied by Riot. Obviously, we didn't have a pit display this year, so we've agreed with Riot that they can do our pit display next year, even if our printing quota is a bit larger. So about the links to learning and project outcomes to this, an innovative project outcome is, of course, our uniform, which, as Ravan mentioned, is made purely out of recycled bottles. This is very innovative, as other teams' uniforms damage the environment because you're creating new polyester, but we're using old polyester, so we're actually helping the environment by wearing these t-shirts. So another thing I want to talk about is something called bootstrapping. Bootstrapping is a methodology that startups use when they're creating their funding for the first round. So this is where they use zero monetary support, like loans. They instead use only in-kind sponsorships and funds from before. That's what we've done, as you see. We've taken our spending to only 482 AD with the thanks of 4 in-kind sponsorships. And yeah, so that's about it. Hand over to Van to talk about our project management.
So these were some documents to show our time management. So this is a Gantt chart and this is a risk assessment. These documents helped us improve our Excel skills and our time management skills.
I'm here in the DT classroom with Flynn, working on our innovative modular car system. There's over 20 different parts that can be added, removed, or replaced. This allows us to achieve unique configurations for our car. This also allows us to change the center of mass by changing the ballast modules, and also changing the wheelbase. And I'll let you in on a secret. Our wheels actually spin. And lastly, we can also change the aerodynamics of our car by changing the 3D printed front sections. Overall, this allows us to create an innovative design for our car.
Our school's 9 meter track, and I'm going to talk about our innovations in car design. So one of our major innovations this year is that we can change the wheel in under 10 seconds. But instead of just telling you that, we're going to demonstrate it. So Vivan here has got a timer, and I'm going to replace that wheel with this wheel with the help of this screw. So let's go. And that's done in 8.5 seconds. That's a new record. So this innovation helps us, well, the judges this year, repair our car if anything gets broken.
These are the project outcomes of our modular car system tests. First, we have the ballast system. 6 is closer to the front of the car, 1 is closer to the back, and we found out that 5 is the most optimal position for the speed of our car. Next, we have the variable wheel base length. We found that a longer wheel length actually dictates our speed quite a lot, and a longer one makes us faster. Next, we have the vector velocities, and we found that if the CO2 canister is farther away from the ground, we actually have a reduction in speed.
And then for this one, I don't think our results were too accurate, but we got the general trend that the more forwards of centre of mass is, the faster the car is. So I think 6 was more of an anomalous result because it's a very funny graph. But it's quite hard to get good tests with all these uncertainties. So I'm going to talk about another one of our innovations, and we've actually got a fun little demo to show you. So this is our car design. It has this funny wing. That one is our car design from last year. It has this ramp system to divert airflow over the wheels. I'm going to say, straight off the bat, that this one is much more aerodynamic than that. So why did we do that? Well, regulations did play a little bit of the part in this. We also encountered a new effect that was due to the Magnus effect. Obviously, we knew about the Magnus effect before, but it's kind of as Newton's third law, for every force there's an equal and opposite reaction. It's kind of like the reaction pair for the force. So let's demonstrate what we're talking about here. So I've got a hairdryer. I'll put it on low speeds to simulate airflow, and Vivan has got our car just over there. So we're going to blow airflow across the front wheel of the car, and you should notice something. As you notice, the wheel starts moving rapidly in that direction, and that's because as the front wing directs airflow up here, that causes the wheel to have to do work against the airflow, which decreases the kinetic energy of the car as it's going into the rotational kinetic energy.
Hi, I'm working on a new YouTube tutorial. These YouTube tutorials help me improve my communication skills. As Aristotle once said, teaching is the highest form of understanding.
Before accounting schools, I had no intention of taking a DT course, but however, after accounting schools, I decided to do DT A-level. And even though I didn't take DT GCSE, my experience in accounting schools really helped that transition feel very smooth. I got the opportunity to apply for work experience at a lab doing a CAD project. I submitted this CAD portfolio, which included all the stuff I've done in F1 in schools, which I submitted at the start of the academic year, and I got the work placement, which will significantly help my university applications.
Next, I improved my skills in graphics design by learning new technical skills that are industry leading, such as Adobe InDesign and Adobe Illustrator. This improved my fluency in creating digital designs that could be used for future-proofing myself.
I improved my rendering skills. I learned different lighting techniques to make the car have a better aesthetic.
I also learned how to use physical analysis tools properly, such as our modular car system, which allowed us to get real-life world physics simulations, and also the Harriet-Watt visit, where we got very accurate results. This allows me to improve my analysis using real-world physical objects instead of only online or software-based simulations.
So to finish it off, I want to say a huge thank you to Yas and Schools for letting us take part in this event. This career over the course of me doing it over 3 years has really helped me, and I want to go forwards and become a mechanical engineer.
For me, I want to become some sort of a graphic designer, maybe for a magazine or pamphlet company, as I think I can really put my 2D vector designs at use there.
For me, I want to improve my rendering and 3D modeling skills during my university course doing product design.
So thank you, Yas and Schools, for letting us take part in this amazing event.